Assalamualaikum, my name is Nur Aintera and together with my group members Muhammad Shazwan, Chen Wei Yuan, Nurul Ashikin and Radato Husna, we will be presenting our laboratory report for polymer processing. Our presentation will cover the introduction, objective, experimental result for every processing method we did. Now, I will begin with the introduction and objective before continuing with the experimental result. Polymer processing is a process to convert polymer material into useful product with desired shape and properties. In this experiment, we study four processes, which is compression molding, screw extrusion, injection molding, and gelling analysis. From this, we can see how different processing parameters affect the product quality. The objective of this laboratory is to study the operating principle of gelling time analysis, injection molding, screw extrusion, and compression molding process. Second, to investigate the effect of processing parameters on polymer behavior and product quality. For the gelling time result, which measure the time required for the epoxy mixture to form a gel. Sample A with a ratio 1:1 gel in 5 hours and 40 minutes. For sample B, ratio is 0.51 took the longest at 7 hours and 34 minutes, while sample C with ratio 2:1 had the shortest gelling time of 2 hours and 43 minutes. This result shows that the changing the epoxy to hardener ratio affects the curing behavior and gelling time of the epoxy system.
Alright, next is for injection molding. Looking at our slide, there is clear improvement from sample A to sample E. Sample A at 10 rpm and 190 Celsius has a rough surface and did not fill the mold completely. However, sample E at 25 rpm and 200 Celsius filled the mold perfectly with an excellent surface finish. This happened because polypropylene is a shear thinning polymer. When we increase the screw speed to 25 rpm, it creates a high shear rate that untangles the polymer jet, making them slide easily. At the same time, raising the temperature to 200 Celsius weaken the force between molecules. Together, this factor drops the mud viscosity, allowing the plastic to flow smoothly and produce a perfect defect-free part. Alright, next is for injection molding. Looking at our slide, there is clear improvement from sample A to sample E. Sample A at 10 rpm and 190 Celsius has a rough surface and did not fill the mold completely. However, sample E at 25 rpm and 200 Celsius filled the mold perfectly with an excellent surface finish. This happened because polypropylene is a shear thinning polymer. When we increase the screw speed to 25 rpm, it creates a high shear rate that untangles the polymer jet, making them slide easily. At the same time, raising the temperature to 200 Celsius weaken the force between molecules. Together, this factor drops the mud viscosity, allowing the plastic to flow smoothly and produce a perfect defect-free part.
Good evening, doctor and my friends. We can look at the first table. The first table is summarize the result of our initial extrusion run. We can see that the sample was processed using a screw speed of 20 rpm. We test three temperature zone in 180 degrees Celsius, 200 degrees Celsius, and 220 degrees Celsius. Based on the visual feedback from the extruded and the condition of the sample, it appears that the combination of 20 rpm and a temperature of 200 degrees Celsius was the most effective, as indicated by the highlighted 20 in the data. This suggests that at this specific speed and temperature, we achieve optimal flow and material consistency. So now we are looking for the second table. For the second table, we increase the processing speed. The setting were changed to a temperature of 200 degrees Celsius and a screw speed of 30 rpm. So interestingly, at this higher speed of uh, 30 rpm, the extrusion process become uh, more challenging. The material flow was less stable, and we observed uh, mention any specific visible defect, dual spell, surface runners, or inconsistent output. This indicate that the increased uh, shear rate at uh, 30 rpm may be pushing the material beyond its optimal processing window at this temperature. That's all. Thank you.
Okay, next for compression molding, we tested five different type of sample, which is sample A, B, C, D, and E. For standard factor, which is sample A, the ratio we use is 733 with weight of 48 grams. For factor of preheat, which is sample B and C, we use different ratio, which is for sample B is 1033 and sample C is 933 with both same weight, which is 48 grams. Uh, then for factor of charging, which is sample D and E, it has a same ratio which is 733, but a different weight which is 55 grams for sample D and 60 grams for sample E. Okay, then for visual observation of compression molding for sample A, we see there is a smooth surface finish and uniform shape. For sample B, it has better flow and improved surface finish. For sample C, it is likely improvement in material distribution. And for sample D, it is increased thickness and minor flash. There is minor flash around sample. And sample E, there is significant flash and dimensional variant.
We are exploring four essential polymer processing and testing methods, starting with the gelling time test. This method is fantastic because it is a simple, low-cost way to get quick data on how fast a thermoset resin cures, which is crucial for checking shelf life. However, it is highly sensitive to operator speed and cannot be used for thermoplastic. You will see this widely applied in quality control for epoxies, paint, and adhesive. Next, let's move to mass production with injection molding. Its biggest advantage is sheer speed and incredible dimensional accuracy for complex shapes. The limitation: the initial mold tooling is very expensive, making it a poor choice for low volume. If you look around you, almost every high volume consumer product, toys, or automotive interior part is made using this exact method. Third, we have extrusion molding. Think of this as a non-stop continuous production powerhouse. It is highly efficient for creating long uniform shapes, but it is strictly restricted to two-dimensional profiles and faces risk like die swell. We rely on extrusion every single day to manufacture pipes, window frames, and even the continuum filament used in 3D printing. Finally, we look at compression molding. This method offers low tooling costs for large area parts and completely eliminates unsightly structural need lines. On the downside, it suffers from slower cycle time and creates material waste known as flash. This makes it the go-to choice for large, heavy-duty items like automotive body panels and industrial gaskets.